become a family member. As an example, this presentation tonight will be on our family's members area in the near future. We are actually having it recorded for you. Eddie is available for a short time after the presentation to sign copies of his books, which can possibly be purchased here tonight. Though I did have 600 teachers here today, and they may have purchased every copy that WA has. Either way, if you'd like a selfie, it's more than acceptable to wait. I'm hoping the young man is in the audience. We are very pleased to welcome Eddie Wu to Perth as our keynote speaker this evening. You may have heard of Eddie, oh God, I can't even speak properly. You may have heard of Eddie through one of his many achievements. WooTube founder, 2016 Choose Maths Award winner, 2018 Australian Local Hero, 2018 Top 10 for the Global Teacher Prize, author, leader of mathematics growth for the New South Wales Department of Education, ambassador for the University of Sydney, or Logie nominated TV star. We thank Eddie for leaving Cherrybrook Technical High School, where he teaches, yes, he still does teach in the classroom every day, to share his passion for mathematics and mathematics teaching for us tonight. And if it is, I must say, if it is anything like the presentation this morning for over 600 secondary maths teachers, it will be amazing. Please enjoy this evening, and could I welcome Eddie Wu to the stage. Thank you.
Wow, what a joy it is to see so many of you here this evening. And as a parent myself, can I say massive respect to all the mums and dads and grandparents in the room who, you know, it was a serious mission to get everyone out the door and on time tonight. So thank you very much for potentially pressing dinner time or squeezing it, and also bedtime on the other side. It's deeply valued. And for me, this is probably my, I want to say, fourth or fifth time in Perth. I was born and raised in Sydney my entire life, and I remember the first time, it was early last year. I was in Kings Park and I was overlooking the CBD, and I thought, man, you know what, I could get used to this. And Sydney is literally on fire right now, so it's really nice being here with all of you. Now, tonight what we're going to have a think about is a world. And I'm just going to start by apologizing as well for the sort of coarseness of my voice. So many of you have been very kind and said hello beforehand. I just get very excited, so I don't have as much voice left as I'd like. But this world that I want to talk to you about, it's this hidden world which has kind of been around us this entire time, but maybe has been invisible to so many of you. And I want to kind of tease back or sort of pull back the curtain and help you understand and appreciate it. But before we get to that, I think I kind of need to address an elephant in the room, which is that, well, I mean, you're all here tonight and you've come here to see a maths teacher. And I sort of am really curious about the conversation you had with your friends or family before you came here tonight and told them what you were doing. Because, you know, if you've been to a concert before, if you say, oh, I'm going to go and see, you know, X singer, band, whatever, then people know what you're in for. Like, I'm going to hear some music. If you're going to see a comedian, I know there's quite a few who play here, you know you're going to hear some jokes. What did you tell your friends that you were going to come and see tonight? It's like, we went for a maths lesson? I don't entirely know. Like, why would you do that? Now, for me, I find it amusing that we have all these different sort of bits of confusion around mathematics because, or seeing a mathematics teacher, because everyone's got a different sense for what mathematics teachers do. I think about my friends, and when we were at school together, I was the only person in my grade who became a teacher, let alone a mathematics teacher. And I think they just figured, are you just going to teach people how to use calculators all day? I have 3 children. They're aged 6, 8, and 11, very similar to many of you here in the room tonight. And I think there's something of a more, let's say, a colorful view of what I do every single day. And I just kind of wonder, Maybe they think like, Daddy, why do you dress up in a tie to just go and count like 1, Like, is that all you do? I think about broader society and like kind of like what's the caricature, what's the stereotype for what a mathematics teacher is and what they do. And I think it's kind of something like this, right? And like, just look at this picture for a second. I pulled this frame out of a movie, out of one section of the movie. Just look carefully, like up here. How did he write that stuff? Like that's just a set designer who went too far. You might think, okay, these are all these different groups of people. Surely teachers would understand what maths teachers do because they work with us all the time. And the answer is sort of. I remember meeting an English teacher at my school once, and he and I were setting up a hall, very much like this one, for an exam. We're about to have a test. We're going to think about how many tables and chairs can we set up in this space so that we can fit everyone in. And this guy's name was Steve. He said, Eddie, this hall looks like we can fit about 16, sort of tables across the front. And I reckon we can maybe go 16 rows back. Eddie, what's 16 times 16? And don't be impressed. It wasn't because I actually mentally calculated this. It's just because I'm a geek and I know the answer to this question. I reflexively said 256. And I'll never forget the look of shock and horror in his eyes when he was like, what dark powers do you have access to? You can just like work out, like that's really messed up, man. I don't know what deal you did with the devil to be able to have powers like that. What about me? What about me as a maths teacher? What do I think that I actually do? I guess, like many people in their own profession, I think I have something of an elevated view of how smart maths teachers are. But I'm just gonna, with all of you as my friends here as witnesses tonight, I'm gonna level with you. I and most maths teachers out there, most of us just spend our time looking like this. Maths is hard. And sometimes we don't like to admit, even as maths teachers, we find it difficult. And I literally, like it's not an exaggeration, I spend a lot of time trying to solve problems, to be able to explain them clearly to my classes, and that's not easy. I spend a lot of time screwing up my answers and trying to work out a new one, okay? I guess what this speaks to, this confusion about mathematics teachers, I think comes to a confusion about mathematics itself. When I meet people and I say to them, I'm a maths teacher, I can see the expression on their face, it usually changes a little bit. They usually kind of frown and their eyes narrow, and I think the reason why is because they attach me, they associate me in their mind with the subject mathematics. And this is what they think that mathematics is. It's just a bunch of weird, random symbols that don't mean anything and have no relevance to our everyday life. And in some ways, this is like a best-case scenario. Mathematics being useless is as good as it gets. For some people, it's much worse than that. For some people, mathematics is a deep cause of anxiety. It's kind of like, oh my goodness, mathematics was the thing I was delighted to be released from when I escaped school. And for me, this is really sad. Mainly because I've now come to learn, much later in life than most people would think, I've come to learn that mathematics is in fact a wonderful and beautiful subject that if you see it right, you can appreciate it. And this comes back to that title that I gave to this session before, The Hidden World of Mathematics. I don't know if you noticed, there was a picture on the slide. It was a canopy of trees that if you imagine like sort of lying on the ground and looking up at the leaves. And those trees were not just any trees. They were actually a very special kind of tree. They were called, or they are called, redwood sequoias. And redwoods are really world-renowned because you can see here, redwoods are really tall. They just go straight up. And in fact, they're not just really tall. Botanists many years ago discovered they're too tall. What do I mean by that? Look closely again at the image. These trees, they just shoot up. They don't become wider at the bottom by very much, even as they get taller and taller and taller. And this seems like it defies the laws of physics, because imagine if the wind should blow. How is it that these very tall trees can stay and not just blow over? They're very tall and narrow. You'd expect them, based on their geometry, to just hit the ground straight away. And the answer for why or how they actually stay standing is brilliant. And I think it's a metaphor for what mathematics is. To really understand the wonder of these redwoods, what you need to do is not just look down at their bases, you need to look down deeper. If you look at a forest of redwoods, and you can see that the topsoil, the ground that's just beneath your feet, if it washes away or if it blows away, what's revealed is this hidden structure just beneath the surface. You can see what's underneath the ground. These are all roots of the trees, and I want you to look closely at them. Do you notice that all of the roots from each separate tree, they're intertwined? And this is actually the key. You see, if you can imagine linking arms with someone next to you, that makes both of you harder to push over, because to push over one of you, I had to push over both of you. When the wind blows on a forest of redwoods, it's not blowing on an individual tree, it's blowing on all of them, hundreds sometimes in a big forest, and that's how they can stay so strong. And for me, mathematics are just like these roots underneath the surface. They're hidden in plain sight. You might have been walking over them for years and not realized they are there. For me, this is what mathematics is, hidden everywhere. And I want to try and use the next 45 minutes to convince you of that case. So let me try and unpack this for you. I want to think about mathematics as more than just numbers, more than just shapes. I've got three particular ideas that I want to try and convince you mathematics is. Mathematics is about what human beings do when we search to really deeply understand and gain insight into why the world is the way that it is. A search for fundamental insight. It's also a source of new perspectives. Sometimes you can understand something better by looking at it from a new angle, and that's what mathematics is all about. And then finally, mathematics is about our curiosity. It's about a spirit of inquisitive exploration that just wants to discover new things, just for the sake of the joy of knowing them. It's a search, it's a source, it's a spirit. Let's start with the top, a search for fundamental insight. Now, mild spoilers. Those of you who got a copy of the Red Book, that's just what I'm going to call it now because I have two books now. Those of you who got a copy of the Red Book may have been having a look at it as you were sitting here waiting for us to begin. And so what I'm about to talk about may be something which you've just read over the last couple of minutes. It all started with a question that my daughter asked me one time when she was probably 5 or 6 years old. So this is a few years ago now. We were driving home. I just picked her up from school, and she said to me, "Daddy, why is the rainbow round?" It had just been raining. The rain had cleared, and there's this beautiful, clear sun shining through the clouds that remained. And there was a rainbow just like this. I mean, it wasn't that actual rainbow. I was driving, so I couldn't take a picture. But there was a rainbow very clearly visible on the horizon, and it had that same characteristic shape that all rainbows do. And it sort of struck me, as all parents in the room know, children are very good at asking questions, and asking questions we don't know answers to. I wasn't surprised that I didn't know the answer to this question when she asked me, but what I was surprised by was I'd never even asked the question before. It's something kind of so obvious. Why is it that this amazingly perfect shape appears in the sky so marvelously after rain? And so I went and did some digging. And to explain what I found, we need to go on a bit of a journey. I want to tell you a bit of a story. Why a rainbow is round has to do with geometry. Geometry is the study of shapes, just like this one. And geometry is an ancient art. In fact, one of the things that I love most about mathematics is that it's timeless. The things that we learn in mathematics, they're true forever. And so we have to go all the way back, if we want to understand geometry, to this guy. This is the person, for every single person in this room, whom you owe either joy or frustration when you studied shapes, because this is Euclid, all the way from 300 BC in ancient Greece. Euclid pioneered the study. We call him the father of geometry. He pioneered the study of the shapes that most of us know when we associate with mathematics. Squares, rectangles, circles, triangles, and all the rest. Euclid was fascinated in these shapes because he kind of viewed them as timeless. People everywhere are fascinated by circles. We see circles in the sky. You just look at the moon. There it is. We love to create patterns out of circles. And as you head out from here, you'll notice all these patterns on the floor, on the walls. We kind of fixate on these beautiful shapes. So Euclid explored this idea, but geometry didn't end with him. It progressed. For example, someone who wrote another chapter in the story of geometry was this guy here. Now, Nikolai Lobachevsky, he said, you know, it's interesting. Euclid was fascinated in shapes that are flat. Squares, rectangles, circles, all the rest. You could draw them on a flat surface. But it's kind of interesting that he loved flat surfaces so much because we don't live on a flat surface. I mean, it looks flat because we're small and it's big, but in fact, we live on a sphere. So Lobachevsky decided to explore the geometry of curved surfaces, like a sphere, like this shape, which he called a saddle, like a saddle on a horse. If you're having a look at this shape thinking, that looks familiar, then you're right, perhaps you're hungry, because this is what we now today know as a Pringle, of course, right? Now, someone just got it, thank you. Okay, now, what I love about this is that Lobachevsky was not trying to solve any problems, he was just exploring. He was just trying to search for insight. It wasn't until this guy came along, who of course needs no introduction. Einstein, of course, he was trying to solve a problem with his amazing intellect. And I just have to pause for a moment to sort of acknowledge his incredible brain, his mind. In fact, he had such a mind that today we associate him with genius. Not even like figuratively, we literally, if you do a Google search for Einstein quotes, half of the quotes that you see next to him, they're not by him. We put them next to him to make them look smarter. It really works. We all get fooled. Now, Einstein, like I said, was trying to use his amazing intellect to solve a particular problem. It was the problem of gravity. Now, gravity might seem a bit of an unusual problem to solve. Why is it a problem? I know what gravity is. It's the thing that keeps me stuck to the ground, right? What's to understand? The thing is, Einstein had some equations that said how gravity should work, except they didn't. It's a little bit like if you've ever done homework and you check at the back of the book to see what the answer is, and you're like, wait a second, that's not what I was supposed to get. Einstein was doing calculations about gravity and its force and its power, and then he would do an experiment. And the answer, the experiment, would not be what he predicted would happen. His equations were all wrong. And then he realized that for most of his work, he'd made an assumption. He'd made an assumption that the universe was flat. The universe is flat. What do I mean by that? I want you to picture, say for example, this floor that we're on right now. It's pretty flat, right? We could build a whole building out of, several layers of this flat structure, kind of like an apartment block, if you like. Lots and lots of flat layers, one on top of another. For decades, people had thought of the universe like that, kind of like a big cosmic apartment block. And all of Einstein's equations were based on this assumption. And then he stumbled on Lobachevsky's equations, Lobachevsky's work with curved surfaces. And he wondered. He thought, what if the universe wasn't flat? I know it looks flat. If you look at the solar system, it's pretty flat. If you look at the Milky Way, it's pretty flat. But what if it weren't? What if, in fact, the universe, space itself, was curved? Wake up, clicker. Ooh, what have I done? There we go. It's gone to sleep, or my computer's gone to sleep. What's it done? I'm going to walk closer. There we go, success. Okay, I don't know if you're just helping me out, Billy, but I'll just pretend that it was me. Can you imagine this quantum leap in Einstein's mind to thinking about the universe like a fabric with very heavy objects like the sun, bending it and curving space, curving time itself. And this is what we now believe. We actually, no, it's definitely not me. I'm going to have to, Billy, click the slide for me. Thank you. This is going to be a long presentation, the rest of it. We'll see what we can work out. We now believe that every massive object, by the way, including you and me, though we're not that massive, not like the Earth or the sun, we all bend space and time around us. This is our understanding of the universe. Do you see what I mean when I say mathematics is a search for fundamental insight to how the universe really functions? Billy, would you click to the next slide for me? He's going to bring another clicker. I think that's very helpful. Thanks, John. Okay, now, I've been telling you this story, all these different people so far. I want to tell you one last person before we come back to the rainbow. Thanks very much, appreciate it. Ooh, this is like a fancy one. Okay, so this, I had to include this because I was telling this story to myself and I was putting these slides together. I thought, gee, I've put a lot of men on this slide and women have played such an incredible role throughout the history of mathematics. They really need to be included. So I want to tell you about this woman. She's amazing. Her name is Mariam Mirzakhani. Now, sadly, we lost Mariam a couple of years ago to breast cancer, which is sad, such a tragically short life. But what was amazing about Mariam is that, well, a couple of things. Not just a couple, but a couple I'm going to tell you about. Mariam was an incredible mathematician. She received something called the Fields Medal. Now, if you've never heard of the Fields Medal before, it's kind of like the biggest prize in mathematics. It's like the Nobel Prize, the Olympics of mathematics. This is it. Mariam was the first woman in history, and currently the only one. She was the first Iranian, and currently the only one, to ever receive the Fields Medal. She received it for her work on something called a Riemann surface. Riemann. A Riemann surface is something that looks like this. It's a weird kind of bizarre-looking shape. Unlike, Lobachevsky's Pringles and Einstein's space and time, these Riemann surfaces look like they can't possibly exist in the real world. They look like something someone just kind of imagined in their mind, which is where these shapes began. Except these shapes do exist in the real world. They exist everywhere, even in you and me. Let me try and illustrate why. Riemann surfaces are tucked away in the most unexpected places. Most of you probably, if I show you this picture, recognize what this is supposed to be. Maybe you can tell me all at once, this is supposed to be an yay, okay, A+, except we're kind of all wrong. Sorry to shock you, but when I went to school, like many of you, I learned this is what an atom looks like. And then I went to become a teacher, and some of my friends who are science teachers, they said, hey, Eddie, we don't want to ruin this for you, but that's not what atoms look like. Atoms, in fact, do not have kind of this nice, neat thing in the center and then these electrons orbiting around in like planets around a sun. In fact, those electrons around the edges, they appear and disappear at random. Sometimes, this is what the mathematics tells us, they're in two places at the same time. How can they do that? And the answer is you can't be in two places at the same time in 3 dimensions. But you can, it turns out, in 9. Now, what does 9-dimensional space look like? And the answer is, it's hard to visualize for us because we live in 3 dimensions, at least we feel that we do. But that hasn't stopped people trying to visualize what these 9 dimensions look like. And what they are is these Riemann surfaces that Mariam Mirzakhani had done so much work in researching. Now, this is what I mean by how geometry literally makes us understand, gives us fundamental insight into the universe and its fabric. You and me are made up of these crazy shapes. Which brings you back to that rainbow I was telling you about. How is it that that kind of geometry, that story I've just told you about, can explain this shape? And the answer is, well, rainbows, that semicircle shape we're very familiar with, are actually not semicircles at all. If you happen to be very lucky and up on top of a mountain or a tower when a rainbow appears, if you're high up enough, you'll see that a rainbow is not a semicircle at all. Just have a look over here. Do you see it extends around until it hits the ground? If you're in a plane or a helicopter when a rainbow appears, if you're really lucky, you'll see that in fact a rainbow is a full circle. It goes all the way around. When I first saw this image, I was like, is that real? Is that computer graphics? Did someone Photoshop that? It's an actual picture taken from a helicopter while in flight. This makes the question even bigger. How can it be that this shape appears? Now, sorry, I did refer to this before. This is what the first proper chapter of my book is about. So spoilers for pages 16 and 17 of my book if you have not read it yet, which is totally fine. This is what pages 16 and 17 show you. They unpack the geometry for why rainbows are round. Every raindrop that is suspended in the sky does 2 really wonderful and important things to the light that passes through it from the sun. Here's the first thing. It takes white light, and as it passes through the raindrop, it spreads out into all of its different colors. We call this refraction. The older folk in the room, like me, may remember that Pink Floyd album cover, which has the light coming in one side, and there's like a little triangular prism in the middle, and out it goes, a spectrum all the way on the other side. And the kids are like, what's Pink Floyd? Is that anyway? Refraction, that spreading out of colors, is the first thing. You can see it there it is, inside the raindrop. But raindrops are not just like prisms. They're round. They're spherical, in fact, very roughly speaking. And so the raindrops not only refract light, they also reflect it back in the direction that it came from. You can see it there on the picture, which is why, let me just go back for a second. Have a look at these pictures. Where is the sun in these pictures? Let me go back to this one as well. This one's a little more obvious because you can see the shadows that sort of clue in where the sun is. Where is the sun? And the answer is, the sun is behind you. Because every time you see a mirror, what you're really looking at is millions of individual little raindrops that are each in their own way a mirror to the sun that is directly behind you. Now, it isn't every single raindrop in the sky that gives you this reflection. Only some of them are in the exact right position with the exact right angle to be able to reflect the sun's light back to you. And those particular ones are all on the surface of a cone. Now, when you look at a cone from the top, you don't actually see the familiar cone shape, like if you're holding a cone of ice cream. When you're looking at a cone from the top, all you see is the cone's cross-section. And as you can see in the illustration, the cross-section of a cone is, of course, a circle. That's the actual rainbow that you're seeing. Now, this is kind of nice, but you probably would be thinking, like, yeah, but I could never have thought of that, right? And it's true, people took a long time, lots of people working together to understand this. But what I want to give you a taste of, very practically, is what it's like, that feeling, that sensation of getting fundamental insight into something. So you and I, are going to play a game. Now, this game that we're about to play requires two things. Number one, it requires you to pair up with someone because it's a competitive game. So maybe you might be playing against mum or dad or a sibling. Good luck with that. Once you've paired up with someone, I need you to choose someone to be player one and someone to be player two. Someone to be player one, someone to be player two. And once you've done that, if you're player one, I'd love you to raise your hand for me so that I know you're ready. I'll wait until half of you have your hands up and then we're good to go. Player one, player one, player one. Okay, outstanding. Hands down. Thank you, player one. I said we needed two things to play this game. The first thing is we need you paired up. The second thing is I need you to break the convention of what's normally acceptable during things like this. I'd like you to do something normally considered very rude when someone's speaking to you, which is I'd like you to please get out your phone. Now, perhaps you're a child and you don't have a phone. I'd love you to please borrow mum or dad's if they are kind enough to let you. And if you get out a phone, let me give you instructions what you're going to do with it. I'd love you to open it up, wake up phone. And once you've got it there, oh, my children, okay. Once you've got your phone there, I'd love you to find wherever it is that you've buried the Notes app. And if you don't know where that is, maybe you're like, I never use that thing, I don't know where it is, just start texting someone. Do me a favor though, don't actually text them what you're about to type because they'll be very confused once they get it, okay? All you need is a space to type numbers, okay? So the Notes app, a message to someone, either will do. Perfect, okay, excellent. Now once you've got that, I asked player one to put their hand up before. Player one, I'd love you to start with the phone in your hand. And here's what I'd like you to do, very simple instruction, okay? Player one, I'd like you please to think, and it's free choice, I'd like you to think of a whole number between 1 and 4, inclusive. So 1, 2, 3, or 4, they're all fair game. Choose one of those numbers, and then, it's not a secret, just type it into the phone display, okay? 1, 2, 3, or 4, type it in. Once you've chosen your number, hand the phone over to player 2. And player 2, once you've got it, can you just hold it up for me so I know you're ready to go? Yeah, okay, fantastic, thank you, phone's down, all right. Player 2, you are going to do something very similar, but with a subtle twist, so pay close attention. You are also going to think, player 2, you're also going to think of a number between 1 and 4, but before you quickly type that number in, instead of typing the number you're thinking of, I'd like you to take that number and add it to the number that's already on the screen. So if your friend typed 2, and you're thinking of 3, I'd like you to type in 5. Does that make sense? So both of the numbers will be there on the screen. Maybe you would just want to put a new line, press enter, type in your new number, and then you can hand the phone back to player 1, okay? So player 1, hopefully you're already or you're shortly about to have your phone back. This is the way the game works. We're going to go back and forth between the two of you, taking turns every time. You're thinking of a number from 1 to 4. Every time you're adding, so they'll get progressively larger and larger and larger. Now, this is almost all the rules of the game, except there's one last rule you need to know, and it's the most important rule, because it's the rule that tells you how to win. Now I've got your attention. Okay, now, the astute among you will have noticed that this game has a name. It's called the game of 23. And maybe some of you have realized why it's called that. Eventually, one of you is going to get to the point where you can type in the number 23. It'll be close enough that you can type in 23. And whoever does that, oops, let's get the next little bit of text. Whoever does that is the winner. That's the goal, okay? And here's what I'm going to ask you to do. I'm going to ask you to finish the game you've already started, and I'm going to give you a couple of minutes, enough time to play at least one more time. When you play again, whoever wins, I want you to swap who's player 1 and 2. So you both get a chance at going first. We want it to be fair after all, okay? And see if you can work out a winning strategy. So play as many times as you can in the 2 minutes that I give you. Good luck. May the best players win. Thanks, everyone. Now, I'm just judging by the volume of noise in the room. I think you have probably played enough to have experienced what I wanted you to experience, and now you're ready to learn something. Now, I'm going to get a bit of audience participation here. I'm going to ask you a question, which requires you to have a look at the phone on which you are playing that game. So don't put it away just yet. Have a look at the phone, and with wherever you played all of the games there, with the numbers in view, I'd love you to answer this very simple question for me. Could you please raise your hand if, at any stage during any of the games, please raise your hand if your opponent ever typed in the number 18. Did this happen to anyone? I expected quite a few. Hands up straight. Okay, all right, thank you. Hands down. Okay, now, that was definitely more than half of you, probably close to 2/3. Even if you didn't raise your hand, just play pretend with us for a second. Just imagine that this is what happened to you. Your friend has typed in the number 18, and then they handed the phone, and it's your turn. Now, for those of you who did raise your hand, I'm just going to make a prediction as to what happened next. I'm just predicting that your friend typed in the number 18, and then they handed the phone to you, and you were about to type in the next number, and then you paused. And then the next thing you said was, I don't want to play this game anymore, right? Because you've just worked out, haven't you, that even though according to the rules of the game's not finished. But the game is over, isn't it? Because no matter what number you play next, they're gonna win, right? Now, what you've just discovered is that when I introduced this game to you, I was lying. This is not the game of 23, is it? This is actually the game of 18. Whoever gets 18, they will always win, no ifs or buts. But hold on a second. Just think about this with me. If the game of 23 is not really about 23, if it's actually about 18, then doesn't it stand to reason that the game of 18 is also not about 18? For example, if you were unlucky enough, for instance, to find yourself playing against me, I like to think of myself as a fairly relaxed, easygoing guy, but when it comes to games like this, no mercy, okay? I'm ruthless. I will do anything to win. Now, if you were playing against me, and we got to a point where I got to type in the number 13, then no matter what number you choose next, choose 1, 2, 3, or 4, I can make my move after yours. I can make my next move 18, and then I win. Wait a second. The game of 23 not about 23, it's about 18. Game of 18, not about 18, it's about 13. Can't I continue this pattern? I can. You know what continuing patterns is called? We have a fancy name for it. It's called mathematics. This is not a game about 18 or 13 or even 8. This is really a game about 3, which some of you may have noticed is something that player 1 can choose on their first turn. So I guess what I'm trying to say is, if you were player 1 and you're still lost, like, congratulations, I guess. I was trying to hand you an unfair advantage and you just threw it away, okay? Now, what's my point here? That sensation that you just got about 45 seconds ago when you're like, that's why my mum kept on winning, right? That sensation of fundamental insight is what mathematics is all about. Now it clicks, now it all makes sense. So, the search for fundamental insight. That was this first idea that I wanted to redefine in mathematics for you. The second idea is that mathematics is a source of new perspectives. Now, my favorite way to illustrate this is by telling you, again, the story of a person whom I love, a mathematician. Though he would never have called himself a mathematician. I'll get to why in a second. Before I get to that person, let's have a look at what's on the screen right now. This is a honeycomb, of course. This is the kind of shape that you find in beehives all around the world. And it's what mathematicians call a tessellation. It's the same kind of shape, a hexagon in this case, copied over and over and over again, and you can just continue it endlessly. It never sort of runs into a wall, the pattern never has to break. It can continue on and on forever, which is why beehives can be of any size. Now, someone who was really interested in studying this was a Dutch graphic artist who went by the name of M.C. Escher. And some of you may have heard of Escher before. Escher was really fascinated by these tessellations. And so he was Dutch, by the way, so when you have a look at this, if you're thinking, I can't read that, it's because it's Dutch. I don't understand Dutch spelling. Now, these shapes here you can see are variations on this same theme. The same shape, copied over and over again, but sort of reoriented and copied and rearranged in such a way to make interesting patterns. Now, these tessellations, Escher quickly realized, provided him a new perspective on the world around him. For instance, he thought about, what if a tessellation got bigger and smaller as you moved through it? So he made this artwork. This is called Circle Limit 3. Now, it's my favorite of his line cuts because when you look at it, it's beautiful, isn't it? I hope you feel that it's beautiful. But it's also intensely mathematical. And it's looking at pictures like this which really gave me a sense for what people mean when they say mathematics is beautiful. I always didn't understand I didn't get it when people said that, right? Now, this isn't where Escher stopped. This is just the beginning. He thought, what else can mathematics give me a new perspective on? One of his favorite kinds of explorations was taking these ideas and pushing them to their limits. Now, sadly, Escher didn't know or didn't have access to the technology that would have allowed him to do what I'm about to show you. But he wrote about this idea in his diaries. He said, this shape here can continue on forever. That's the whole idea of a tessellation. And so it took until only about 5 years ago for us to take that idea and then give it a real physical expression. This is Circle Limit 3. But not any Circle Limit 3 that Escher could have created back in the 19th century. This is what it looks like to move through Escher's artwork, to travel into it and to move through it. Now, I'm just going to give you a bit of a warning. If you're the kind of person who experiences motion sickness, you may like to turn away right now. But for the rest of you, I just want to stand back and let you enjoy. Now, what are you looking at? For a moment, your brain gets confused. Because moving through this space doesn't follow the rules that moving through other spaces does. For example, parts of it, I'm just going to move this out of the way. Sorry, Marwa team, just so that everyone can see it. Moving through this space, you can see some things change, but some things stay the same. For example, just look closely at that big circle right there in the center. Can you see it's moving, but it's also kind of standing still? You see, moving through a space like this follows different kind of mathematical rules to the space that you and I are used to in our everyday lives. Now, this idea here of projecting something that's 2D, Escher's work was 2D, onto something three-dimensional, this is something Escher was fascinated by. And one of his artworks demonstrates this really clearly. Escher did a bunch of self-portraits. That's Escher right there in the center. And you can see his reflection in a silver ball that he was gifted right beside a glass ball and another ball that's opaque. Don't look at it too hard, by the way, because if you look closely in the middle, you'll see in the reflection next to Escher, this is the picture that you're looking at that he's drawing. There's a picture of the picture that he's drawing in the picture that he's drawing. I told you not to think about it too hard. Okay, now, what I want you to look at closely is that behind Escher's head in the self-portrait, behind his head, just up here, you can see the ceiling of the room that Escher's sitting in. Can you see it? Yeah? Now what's amazing is, so many of you said, yeah, I can see it, even though that doesn't look like any ceiling in any room you've ever sat in. Because a ceiling is usually rectangular, like the room that you're in. But that's no rectangle. Your brain kind of perceives it as a rectangle because our brains are really good at sensing when something has been distorted. Look more closely at it now. It's nothing like a rectangle, is it? It's all curvy and weird and bendy, right? Have a look at the window next to Escher. It's even weirder. It's even more twisted. Now, like I said before, this idea of taking a flat thing and putting it onto a curved surface, we call it projection. And projection, I'm just going to make a bold claim. Projection will change the way that you look at the rest of the world for the entirety of the remainder of your life. From the end of 5 minutes from now until the rest of your life, you're going to look at the world differently. That's a big call, isn't it? Let me try and explain what I mean. This is a beautiful map of the world. I love this map of the world. It's very common, this particular map. I love it because it's made of satellite photography, so you can see where the ice is, you can see where the forests are and the deserts and all the rest. The only problem with this map of the world is that it's not a map of the world. This can't be a map of the world, and I'll explain why. This is a two-dimensional rectangle, right, which we use to illustrate what the world looks like. The problem is, of course, that the real world is actually, well, it's round, right? Now, if you imagine taking that globe up there and taking a pair of scissors and cutting off the surface of the globe and then laying it flat on a table, you would not get that map that we saw before. In fact, what you would get is something that looks much more like this. Now, this is accurate. This is a map of the world. It's just not very useful. Of course, you've got these weird-looking curvy shapes. These are called gores. You might recognize this, by the way, as the SBS logo. It's 4 of these gores tilted on their side because it's meant to represent the world. The problem with these gores is that even though they're accurately representing the geometry of the Earth, there's all these big gaps between them. So this map is not very good for, like, navigating, right? The UK, for example, they're currently going through Brexit, but somehow I don't think that's exactly what they mean. Now, mathematicians and cartographers alike thought we can fix this problem. What we'll do is we'll take those gores, those parts of the map up there, and then we will stretch them to fill those white gaps. Pretty clever, actually, when you think about it. And that's why a guy named Mercator, he created this. It's called the Mercator projection of the world. It's not really the world, but it's a version of the world. However, now that you know how Mercator made his projection, maybe you're seeing the big glaring problem with it. For example, I don't know if anyone in the room here has been to Antarctica, but you probably are looking at it thinking, was it always that big? Like the size of every other continent on the planet put together? That doesn't look right. You're right. It doesn't look right, and the reason why comes back to this projection. Have a look at it. Can you imagine taking a balloon, right? And then, like, before you blow it up, you draw a smiley face on it, and then you take it, put it to your mouth, and then you blow. What happens to that smiley face that you drew on the balloon when you inflate the balloon? It gets bigger, right? Because the balloon that you drew it on also gets bigger. And that's what happens with this map. To stretch out and fill those gaps, you have to make parts of the world bigger. Some of these parts are more obvious than others, like Antarctica. Antarctica is right at the bottom of the planet, so you have to stretch it out a lot to fill the gaps. And so, in fact, the real sizes of the continents are nothing like this. These are the real sizes of the continents. Now, I know it kind of weirds you out when you first look at it because, hey, what's going on? What's happening with the countries there, right? But what you're realizing right now, what you're experiencing, is that the world you thought you knew has been an illusion this entire time. This is the world as it actually is. Pay close attention to that landmass right at the top. It's Greenland. Greenland, because people have a sense of humor, Greenland is not green. That's Iceland, that's Greenland. Go figure, okay? Now, Greenland looks enormous, right? It looks like it's twice the size of Australia. But when you have a look at the real size of Greenland, you realize it's teeny tiny. It's about the size of WA just by itself. Now, I said before that this would change the way you look at the world. The Mercator projection that we're so familiar with, it's the most common map in use today, is just one of many. There are projections that serve different purposes that are suited to different kinds of designs and different people who are using them, depending on what your perspective is. And this is what mathematics is to me. It's a source of new perspectives. Now, I want to illustrate this with a practical example, just like I did before. But we're not going to play a game this time. I want you to think about this photograph with me. Now, this photograph, I really love this photograph because it looks hilarious. What are these two people doing? They kind of look like they're dancing, right? Like it looks sort of like the Michael Jackson Thriller move. Like, do you know that dance move? Okay, yeah, you know the one. Okay, now it does look like they're dancing, but they're not dancing. They're posing. They're posing for a photo because they're in a very special place. They're not here in Australia. They're in Italy, and they're posing next to the Leaning Tower of Pisa. Some of you who have been there maybe could have guessed that because you're like, I also looked stupid doing that pose, right? Now, what I love about this picture is that this picture we're looking at right now, this is not the picture they were trying to create. It's taken from the wrong angle, right? But what I love about this is that taking pictures of people from the wrong angle, it's kind of become a subgenre. Taking pictures of people at the Leaning Tower of Pisa. If you look closely, this one here, you've got this guy who's doing the classic, whoa, and then you've got this guy kind of giving him a teeny high five with his finger. I think that's cute. And then, of course, there's this guy who's showing the size of this guy who's showing the size of the Leaning Tower. Now, these are funny. It's a whole wonderful subgenre on the internet if you want to go and search for them. This is not what they were trying to do, though. Of course, what they were really aiming to do was this. Now, I love these photos. Like, even though we know they're not real, they're so well done. And I can only imagine how many shots it took them to get these photos. They're so well done that our brains are kind of sort of fooled, aren't they? I mean, we know that there's not some enormous woman who's about to carry off the Leaning Tower of Pisa, thank goodness. And yet, when we look, it's kind of like, wow, but it looks like there is. Okay? Now, why is that? How is it that these pictures can fool us? And the answer is because pretty much everyone here in this room, it seems to me, has two eyes. And that's how we experience the world. We experience the world through what we call stereoscopic vision. Stereo is in like two, like left and right, like speakers, okay? Now, I want to give you, like I said, a live demonstration of this. Stereoscopic vision is amazing, but it's not perfect. I want to illustrate to you why. To do that, you need your index finger. What I'd like you to do is to hold up your index finger in front of your face, hold it up about, I don't know, a comfortable length, maybe 20 centimeters in front of your face. And what I'd like you to do is position your finger such that you can look closely at your finger, and I'd love you to focus on it, but position your finger such that you can see me behind your finger, okay? So you might need to, if you're on the side of the room, you might need to tilt in a little bit, okay? So hopefully you can see your finger clearly. And then behind it, I'm waving at you. Don't look at me, look again at stay focused on your finger. Behind your finger, you should see me, and I'm all blurry. Is that right? Your finger's sharp, and I'm blurry back here. If I'm not, please go and see an optometrist because there's something wrong. Okay, now, stay looking at your finger, keep your finger there, and now, with your finger in that position, don't move it, I now want you to shift your focus to me. Now, if you're looking at me, here I am, now I'm sharp, and now your finger's blurry, but your finger's not just blurry. Did you notice? Your finger's done something else. There's two of them, right? Now, you can prove this to yourself by closing one of your eyes, still look at me. Oh, thank goodness. You've got one finger after all, it's okay. Now switch eyes. Whoa, what's your finger doing? Are you moving your finger? No, you're not, but your finger looks like it's moving, so what's going on? Okay, you can stop doing that because you look hilarious. Okay, now, what's happening? Why is your finger teleporting? And some of you have worked it out, right? Your two eyes are seeing 2 images of the world every second of every day. And our brains so intelligently stitch those 2 images into what we call single vision. Sometimes it doesn't do it quite well, and so we call that double vision, when your 2 images are not syncing up in your brain. Now, the reason our brain does that, rather than just having like one eye that can just see the world, that would have been simpler, right? The reason it does that is because stereoscopic vision is the key to perceiving distance. It's how you can know whether something is big and far away, or small and close up. And that's the secret to why these pictures are so perplexing. See, when we look at these pictures, we're not in Italy right now. We're in Perth, looking at pictures of people in Italy. So your 2 eyes, if we were there, would not be fooled, because our 2 eyes can perceive the depth and we can see that there's a difference there. But right now, your 2 eyes are not seeing 2 different things. They're seeing both the same picture. So the cues that our eyes use to perceive depth and size are all being short-circuited. What your brain is basically doing is comparing the angles between, where your finger was to know, oh, the angle between those is really large. That means it's close up. Your brain has been doing trigonometry, this measurement of angles and distances and lengths relative to each other, every single moment that you've been looking at something just without you realizing. This is why mathematics gives us a source of new perspectives even when we don't recognize it. So, it's time to land the plane. I promised a search of fundamental insight, a source of new perspectives. Does anyone remember what the last one is? A spirit of inquisitive exploration. Now, let me explain what I mean by this. In mathematics, we often do maths to solve problems. We call this applied mathematics. You're like, I want to build a bridge. I want to make sure that I make a profit with this business. So we use maths to help us solve a particular problem in a particular situation. But sometimes maths is not for solving a problem. Sometimes maths is just because we're inquisitive. We're trying to explore and discover new things just because. And this is a perfect example of that. What you're looking at on the screen here is called the Borromean rings. These are a really wonderful shape. It's not just like, 60% of an Olympic logo. These are actually special in and of themselves. The Borromean rings are special because, look closely at them, even though they are 3 separate rings, you can't ever separate these rings from each other. They're kind of intertwined, right? In fact, that's the reason why I have a friend and his wedding band is made up of 3 separate rings that are sort of joined together in this way. One of the rings is white gold, one is yellow gold, and one is rose gold. And the whole point is it's a metaphor. You can't separate the rings, just like you can't separate him and his wife. It's very sweet, right? Now, here's the thing about the Borromean rings, though. Here's the weird thing about them. Have a look up at the screen, and you can see there's 3 rings, one red, one blue, one green. What I'd like you to do is to, in the quiet of your own mind, choose one of the rings, the red or the blue or the green one. And I wonder if you can use your imagination and make that ring, the one you've just chosen, can you make it disappear? Can you see this image without that ring in the way? Now, it takes a bit of mental concentration, but once you do, if you can make it disappear, you might have noticed something unusual happened. If, for example, you made the red ring disappear, you might have noticed the blue and the green ring, suddenly, they just have nothing to do with each other. They can just float apart. And it's the same with the green ring, you made that disappear. The blue and the red suddenly have no connection whatsoever. Their link has to do with all 3 of them simultaneously. Now, mathematicians looked at that and they were like, that's weird. I want to understand that. And so they do what all mathematicians do. They said, well, let's simplify the problem. So they simplified it down and said, well, if 3 rings are hard to understand, let's start with just 1. This is 1 ring, okay? And they studied it in this field of mathematics called knot theory. Most of you have probably never heard of it because it's not something that we study mostly in mainstream maths. And it's because it doesn't have many useful applications, at least we didn't think so. This guy here is called the trivial knot, because it's a knot just like, the shoelaces around your foot, but it's not much of a knot at all. There's no twists or turns in it, okay? Now here's the tricky thing about knots. Some knots look different, but they're actually the same. For instance, this knot looks different, doesn't it? It's got some extra 12s in it, but in your mind's eye, you can probably use your imagination to untwist those two loops in the bottom left-hand corner, and if you do that, what do you end up with? The same trivial knot that you had before. Even when it looks terrible, like this monstrosity here, this looks like what happens to my headphones when I leave them in my pocket for too long, right? But with time and patience, you can take this same knot and untwist and untangle, and sure enough, it's the trivial knot just like we saw before. But not all knots do this, okay? Even though this one looks simpler than the one I just showed you, this is a truly different knot. This is called the trefoil knot. The name comes from tre as in three, and foil, like the word for foliage. This is the three-leafed knot. Now, no matter how many times you twist and turn this, you'll never get back to the trivial knot. And the reason I know that is because I tried. Now, this is a skipping rope that used to be useful as a skipping rope, and then somehow my 6-year-old son, he, with superhuman strength, ripped off the handle from one side. I was like, well, this is no good for skipping. So I cut off the other side, and then I reattached the ends in the shape of the trefoil knot. Now, I want you to pay close attention. You see I've highlighted 3 spots on the knot. These are the 3 spots where the knot crosses itself, okay? It's what makes the knot what it is. 3 spots where it crosses, and no matter how many times you twist and you turn, there are always going to be those same 3 crossings. And believe me, I tried. I had a lot more than just these 3 photos of me trying to do different versions, okay? Now, once you realize you can do 3 crossings, there's no reason why you can't do 4. This guy, again, mathematicians aren't always very creative in their names. This is called the figure 8 knot, because there's a figure 8 right in the middle. Once you've got 4 crossings, you can have 5, 6, 7, as many as you like. Now you're probably thinking, Eddie, like that's nice, but this is kind of what I hate about maths. It's pointless. Like it doesn't go anywhere, right? Like what's the usefulness or the relevance of this? And well, it might not necessarily help you balance your checkbook or build a bridge, but I'm not exaggerating when I say your life and mine depends on these knots. What do I mean? Are there any identical twins in the room? Anyone? 0 identical twins? That's interesting. Usually in a room this size, I get 1 or 2. Oh, 1? But your twin's not here, is my guess. Okay, all right. Sorry, that's fine, that's fine. So that means that even with our friend in the room, every single person in this room is separated, is distinguished from the other people in this room, since your twin is not here, by the fact that you have a completely unique genetic code. Deoxyribonucleic acid, more commonly known by its acronym DNA. Now, you've got DNA. This code makes you who you are. There's a copy of your DNA in every single one of your cells. And DNA, even though it's tiny and microscopic, this is just an artist's impression, it's tiny and microscopic, but there's so much information required to make you, you, that if I were to take the DNA out of just a single one of your cells and lay it out on the floor, there would be 2 meters of DNA just in a single one of your cells. 2 meters. Just in one. Now, what does 2 meters look like? Well, my friend Oliver from Sydney Uni, he is exactly 2 meters and 1 centimeter tall. I'm about 178 centimeters tall. So you've got an Oliver's worth of DNA in every single one of your cells. That's a lot of information, okay? And here's the thing. You're not just a one-celled organism. And last I checked, there were no amoebas in the room. So you're actually made, on average, of 37 trillion cells. So, if I took the DNA out of every single one of your cells, don't worry, I won't do it. It would probably hurt if I did. I'll leave it where it is, okay? But if I were to take all that DNA out and then lay all of it end to end, it would stretch out 74 billion kilometers. So, yeah, right? Okay, 74 billion kilometers. My goodness, like that's a length. That's a distance that's too large for me to really comprehend. Like when I was in year 11 and 12, I ran the cross country at my school. It was 6 kilometers. I almost died. That's the longest I can, consider. What does 74 billion kilometers look like? Let me try and illustrate for you. The sun. It looks pretty small in the sky, but the reason is because it's far away. Right? The sun is in fact enormous, and to give you a sense of its scale, I just want to play this little video for you while I talk over it. This is the transit of Mercury, that little ball you can see in the bottom left-hand corner. That's an entire planet moving across the face of the sun. We don't get to see the sun from this angle usually. We don't get to reckon with how enormous and scary that it is. The reason why the sun just gently warms us is because the sun is so very far away. How far? If you were to travel all the way to the sun, the surface of the sun from Earth, and then travel all the way back, and then repeat that journey, that round trip, 250 times, that would be 74 billion kilometers. You've got enough DNA in you to go to the sun and back 250 times. How's that possible? How can all that DNA fit inside you? I know some of you are thinking, well, I knew I gained a few pounds this summer, but I didn't think it was that bad. How does it all fit? And the answer is, you should have known from the beginning, right? All that DNA, it's in knots, all twisted and tangled inside your cells to keep you alive. In fact, there are enzymes in your body, and their sole purpose for existing is to untie and retie your DNA into different knots for different purposes, like replication. I'm not exaggerating, to keep you alive. To me, this is why mathematics is amazing. It gives us fundamental insight into why the universe is the way that it is, sometimes in really surprising ways. It gives us new and brilliant perspectives on this world that we live in, and sometimes tells us our perspective has been wrong and we need to amend that. And lastly, it's about this spirit of inquisitive exploration. It's about the willingness to be curious and to just explore the world. That's what I love about this hidden world of mathematics. Thank you.
I can't imagine that there were too many parents who thought that on a Monday in November, they would find themselves at Crown Resort, not in the restaurants, not in the casino, but sitting in a room to listen about mathematics. I'm always impressed by the way that mathematics explains everything in the world. And yes, I'm quite open to admit I am a mathematics teacher. More important than that, there are many mathematics teachers in this room, and that is the parents of our children, because you are the first mathematics teachers in your children's lives. And so I'm going to ask Holly to find a spot in the room. Get your act together, Holly. Okay. Holly is standing next to one of our young audience members, and I'd like that young person, if they could make their way to the front, please, because I'm going to ask Eddie to present this person with a free gift of a signed book this evening. Now, of course, this young lady's mum and dad, you are more than welcome to come up and take a very close-up selfie. Here we go, guys. Yeah, you take that.
I've trained professionally to turn his mic back on, except Billy's shut me off. Yeah, that's fine. I'm usually on, in a school, I'm usually on the other side, kind of like, oh, yay, this is nice. But I know I've got to, hold on. I think I have to shake your hand. There we go. And then you get to hold this bit there. There we go. There we go. Let me come a bit lower. Thanks, Keisha. Enjoy.
Thank you so much for joining us this evening, and I hope you leave the room. I know I certainly will. Those photos of my husband and I kissing over the pyramids in Egypt so don't have the same effect anymore. Thank you very much for joining us. As I said earlier, Eddie will stay around just outside to sign books, take photos with the children. Thank you so much, and I hope you've enjoyed this evening.